VNS tomography in Phoenix is pretty similar to VNS tomography in Flatirons. Let's go ahead and create a new VNS tomography model. Give it a name. We'll just do demo. And horizontal node spacing. For this survey, I'm just going to choose something fairly coarse because this is just for demo purposes. And like Flatirons, you give it some sort of initial velocity field. Like Flatirons, it converges very fast, so the initial model is somewhat important. Now, as far as the vertical node layout, you've got two choices. Traditional VNS is really, I should have called that just, Flatirons VNS. You give it a spacing at the surface and at max depth, and then how deep do you want to go? I pretty much never use that version. I use the flat bottom VNS. You give it the bottom elevation. Our survey goes down, or it starts at about 3,000 foot of elevation. So I'm going to go down to let's say 500 feet above sea level. What's the ratio of the deepest node spacing to the shallowest node spacing? I'm just going to leave the default 3. That seems to work well. And then how many vertical nodes do you want? Again, as a first pass, you may want to reduce that to something even more coarse, like 20. For more detailed work, make it 40 or 50, but I'm going to leave it 30 for now. One huge difference between Flatirons and Phoenix: Phoenix does not allocate memory where there is no data. Phoenix actually looks at the ray path coverage for the whole survey and only allocates memory at those locations. And that implies that the angle of the grid is not really that relevant in Phoenix, unlike Flatirons. If you want to, you can change the angle, or you can just leave it the default. It doesn't really matter that much. It won't change your solution that much. Let's click on OK. And again, have to open in the tab. And it looks similar to the delay time tab, somewhat similar. Very first thing you're going to have to do is run an analysis. And by default, Phoenix does not overwrite your current solution. In that way, it's very easy to update a model, and if you don't like the update, go back to the original model. It's just much simpler and cleaner than Flatirons. Minimax offset range, pick decimation by default is 2. We'll leave it at that. That's actually fine. Number of iterations is also fine. Right now you can apply a constant VTI terms, delta and epsilon. If you do choose to apply these, I think Flatirons has the same option. You will get different results, and it's quite interesting. And in my experience, the results with VTI do tend to look a little bit better in some cases. Forthcoming in Phoenix is a full VTI inversion, but that's several months out. Go to the next tab, and very important, be sure you pick the correct pick version. I think we have nearest time picks from our delay time work. I'm going to go ahead and use those. Even though there's no inner offset picks, for this demo, I'm going to go ahead and use the nearest time picks. The residual statics constraint option, I recommend not using this option right now. We are currently implementing a full-blown, full joint inversion of residual statics and tomostatics, and it should be dramatically better. And this option is going to go away in that case, and that's about 2 months out. HTI anisotropy, it can give really interesting results. I haven't seen them improve the statics, but they look interesting. I'm not going to use that in this case. Sometimes if you can't track the first arrivals across certain offset ranges, like if you've got shallow inversions in the near surface, it can be really hard to track events consistently. And you just say, I'm not going to use picks within this offset range. I'm not going to choose that option in this case. Velocity constraints. I always recommend the first pass force the velocities to increase with depth, and then give it some sort of offset range, or a velocity range. This is the coolest feature in tomography in Phoenix. If you have external information, for example, uphole survey or gravity data or FTG data, You can use that to constrain the inversion in Phoenix and get some really fascinating results. Unfortunately, this survey, I don't have any external data, so I'm not going to use that constraint. And this will be covered in another video as soon as I have appropriate data. Depth weighting scheme, very similar to flat irons. Leave the default, it works great. I should hide this dialog. And additional velocity constraint, how do you want to smooth it? The default 1 is fine. I never smooth vertically, I'll leave that one off. And then how do you want to interpolate the velocity field into the low rate path coverage areas and low fold areas? Again, these defaults are going to be fine. If you're in meters, you may want to change the 2000 to say 500 or something. And the final tab, how do you want to run this? Do you want to run it on the local machine like flat irons? More often than not, you can do that. And if you have availability of an MPI cluster, you can do that. And this current version of Phoenix uses OpenMPI version 1. If you have a different version of MPI, it's trivial to compile Phoenix with a different version. We've done that for a number of customers. All right, I'm going to click Finish and then pause the recording while this very lengthy process runs. Okay, we're back. The Tomo has finished running. Once it's done, you have to manually reload the list of available models. Once you do that, you can open up the new VNS model. And again, you can see that you have a bunch of tabs up here with any number of VNS models, delay time models, pickers, or whatever. Okay, let's go ahead and take a look at it. Let's go down to Layer from 3D Volume. This is the surface velocity, and you can select any kind of depth range you want to QC. Left click and drag in this display, and that will show you the profile in this display. This is a little bit different than the flat irons version. By default, you get 3 panels. I usually close the 3rd panel, and the 2nd panel down I will have as the hit count. And I'm going to change the color scale so it's a bit cleaner. Right click on the colors and select this white, gray, red, yellow display. And you can see this is showing you that you've got like one big booming refractor in this geology. This is where the hit count kind of piles up down here. And you can go back to the map and look at different profiles, but they all look pretty much the same. This is very, very simple data. Okay, so once you've done that, it's very trivial to compute statics. You simply have to pick your intermediate datum and a final datum and a replacement velocity, and then that's it. I'm not going to bother to do that in this case, though. All right, so one thing you can do in Phoenix, which you cannot do in flat irons, which is actually extremely powerful, are shot station tomography stacks, this tab right here. It looks just like the stacker in the delay time tab. Works a little bit different though. Let's go ahead and create some new stacks. I'm going to go ahead and call it Pass 1. So you're probably wondering why we bother to create tomography stacks, shot receiver tomography stacks. There's 2 reasons. One reason, it's a great QC for your tomography model. I mean, do the stacks line up close to 0? And the other big reason is once you have these stacks, you can go through and pick them like you do the delay time stacks and use those picks to modify the velocity field. This is kind of like a cheating method for updating the velocity field, like with residual information. It works very well though. And when this is done, I'll come back. Okay, the stacks are finished. Click on OK. And this is what we looked at, what it looks like. I realized after I clicked on OK to start the stacks that I hadn't selected the correct offset range. By default, it's quite shallow, 1,000 to 6,000. And I should have gone deeper than that, maybe 3,000 to 6,000 or something. These inner offsets just don't have any valid data, and that's why these stacks look like that. But anyway, you can still go through and see how the stacks look, how they vary across the survey. You can pick it, and once you've picked it, just like the delay time solution, you go to the up arrow tab, the second from the left, and update the model. And Phoenix will force you to create a brand new model. It will not overwrite your current model. You tell it, well, how deep do I want to modify this model? The assumption being that these stacks are reflecting issues in the shallowest few hundred feet of your survey. And just like the delay time solution, you select your pick version and an update percent. You click on that, and it will create a new model. It's very simple. Once you have a new model, you can go through the same procedure, create new stacks, and iterate. I've done this on a number of surveys, and the statics improve significantly in about 80% of the surveys I've tried it on. One final thing you can do is, I'm going to open up a picker window, select a shot, and I'm going to turn off the delay time solution, and I'm going to go ahead and group things by the line number, the station line number. And finally, I'm going to add move out, VNS travel times, and select the correct model here. And then you can step through your traces and see how things actually do flatten out. You can see that these picks are wildly inaccurate. And this is not the best survey to demonstrate the VNS tomography. We'll have better data later, and I'll redo the video. But just as a brief tutorial, that's how you do VNS tomography.